Hey teammates, how you doing? We're back again with Simple Harmonic Motion Part 3. This is to follow on from our understanding of the term omega, angular frequency. Now here's a situation where we have simple harmonic motion. This is the X graph, okay, showing what goes on with where the thing is over time. And how we can show this in terms of the mathematical equation is that X equals A sine omega t. And don't forget that omega, alright, is to do with the period that it took, okay? And omega equals 2 pi divided by that period, okay? It's how fast it goes up and down. Obviously, if it goes up and down faster, then omega will be a bigger number, okay? And we should think about that too for just a second. That might be useful, okay? So if we have a situation where, how am I going to do this? Okay, we have a situation where we have something with a high angular frequency. It's going to go up and down very fast, okay, over time. Whereas comparatively, if we have a low omega, it could take a long time period, okay, for the same thing. So short period, big omega, long period, short omega, okay, just to give you an idea. Now, here we go. That's the X value thing. Now, as we hopefully remember from motion, okay, if we've got a graph we want to show velocity over time, it's totally connected to the displacement graph, all right? Now, important stuff's happening here at the maximum displacement, as we talked about originally, at the point where the thing is going through the middle, at the maximum negative displacement, and back to the middle again. And while we're here, we have the 0 point. Okay, now if you can visualize once again the spring going up and down, let's see if we can find that little fella again. Here we are. Oops. Okay, I'll get rid of that. Did I do it again? I think I did it again. Great. Bloody hell. Okay, so here's a situation where the thing is going up and down. Now at the top of its displacement, 0 velocity, at the bottom 0 velocity, and in the middle, maximum velocity. So let's show that in our graph. It shouldn't be too hard. Whoops. Okay, so here we go. We've got, once again, okay, at a maximum displacement, we showed it stops. It's got a 0 velocity. At the minimum, or the maximum negative displacement, it stops. It's not going anywhere. Now when you think about this, if the little mass we've got is going upwards to stop, okay, and it's in the middle of that motion, so it's basically, it's gone from the bottom, we've let it go and it's gone up through the middle, it's going fast here, and it has a positive velocity. It's actually going the fastest possible it can go. Then it's coming downwards here, quickly, we must have a maximum negative velocity, and then it's back. When it gets slow, stop, here's the 0. So we have this equation here, or that graph. Then as it's going up again, it comes up to a maximum positive again. So it looks the graph a bit like this, okay? Now hopefully you realize this form of a graph is a cosine. Now we keep the cosine omega t going on because the angular frequency of this graph, okay, is the same as of this graph. It still takes the same amount of time to have done one complete motion, right? So because the period is the same as here, the angular velocity is the same. Now that's great. But if this is a velocity graph, the maximum velocity value, okay, is like V max, if you like. Now, we don't have to know the maths behind this. High-level guys will do this, but we can also show the derivative of this, the rate of change of this thing. And if you do the rate of change of a sine formula, this is what it looks like. The amplitude, which was here, is connected to this amplitude, but we have to actually put in the amplitude and an omega out the front. So the new V max, okay, is the displacement amplitude times omega. And when you think about it, this makes a lot of sense, okay? The reason it should make a lot of sense is if we have a big omega, okay, think back to what we looked at before, whoops, when we had, how are we going to do that? Okay, think back to what we had before when we had the really big omega, right? It's going chung 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 chung. Now, big omega, in this case, you can see it. It's got to be going up and down. Oops! It's got to be going up and down very fast. So big omega means a big velocity. Okay, a big V max. Let's try that again. So a big omega means a high velocity. It must be screaming along to be going so fast here. So V max must be big, and it depends on the big angular velocity. So that's why angular velocity has something to do with the maximum velocity, okay? If our thing was going along very slowly, on the other hand, okay, we've got a low value for omega, so the thing is just lazily going up and down. The maximum velocity is now going to be small, okay? Hope that makes sense. So now we've got two equations, okay, for the displacement and the velocity. Now let's keep going. The last one that we have to worry about, as you know, is the acceleration. Okay? So let's get cracking. We have to think about where is the velocity changing the most. Now you hopefully remember from mechanics that the acceleration is the change in the velocity over the change in the time. Okay? You can also think about this because the sum of the forces is mass times acceleration. Hopefully you remember from the first video that the forces aren't balanced at the top or the bottom of the motion. So at the top or the bottom, the acceleration is going to be a maximum. Okay? So now let's think about this. Let's say we pull the spring down to the bottom of its path. So we're basically like starting here, right? Now at that point, at a maximum negative displacement, the spring is stretched and it will be pulling upwards. Okay, so the sum of the forces is going to be a maximum when we pulled it to the bottom. At the top of our thing, the sum of the forces is going to be a maximum downwards. Now if the sum of the forces is a maximum downwards, the acceleration must also be a maximum downwards. So along this line, if we keep going, okay, let's extend this line down. At this point here, the displacement is a maximum. Okay, therefore, at this point, okay, the acceleration we've said already is a maximum downwards. Remember, let's have a look. At the top of the motion, the acceleration is a maximum downwards. Now remember, downwards is negative because upwards is positive, right? So at this point here, we must have a maximum negative acceleration. As we said before, when the thing gets to its midpoint, okay, we should really draw a nice big long line all the way down here. When it's in the middle of its velocity, the velocity, middle of its motion, okay, x is 0, the velocity is maximum downwards, but there's no forces in the spring. It's all balanced, right? So at that point, the acceleration has to be 0. Okay? Just as we have at the beginning of the graph, here, 0x means the forces are in balance, so we must have a 0 here. Then, when the thing has gone up, and then like up, and then down, and it's down the bottom and it's stopped, but it is maximum stretched downwards, as we saw, the sum of the forces is up. So the acceleration is positive, and it's at a maximum because the spring is stretched at a maximum. So at that point in time, okay, if we draw our line a bit further down, even though it's at the bottom of its motion, the acceleration is upwards because the force is upwards. okay? And then we get back to the point where it's in the middle, and acceleration is 0. So that should hopefully make sense why the acceleration is the values it is at different points on this motion, okay? And what we have here, as you should hopefully know from maths, is a negative sine graph. So there'll be a negative term, okay? Then there'll be a sine value, and once again omega t doesn't change because once again it's taken t, the same period as it did before, to do this one motion. All we've got to worry about is this first bit here. Now, how big is that? Well, once again we can do the situation where we have we can use maths, and if we use maths to differentiate this equation, we've got to once again take the omega value out and put it at front, and we end up with negative a omega squared now sine omega t. So the acceleration is totally related to the omega, and that makes sense once again. If you imagine a big omega value, okay, you've got a situation where we just said where it's going up and down very fast. If it's doing that, you can imagine that here, when it's changing its velocity and its direction so fast, we must have a large acceleration. And the acceleration is actually proportional to omega squared. Okay? Also, if the amplitude of our initial thing is big, the forces are going to be very big because we've stretched our spring. Therefore, we're also going to get a large A. If it lazily changes its position, it lazily changes the forces, so it'll lazily change its acceleration, and in this case we'll have a small acceleration. Okay? So what we end up with, in summary, is the following. Get rid of that. Okay. This is what we end up with. Alright? X is equal to sine omega t. Velocity is equal to, oops, we forgot the A. A omega sine omega t. And acceleration is negative A omega squared. Oops, I made a mistake. That's not a sine, is it? It's a cosine. Negative, oh hang on, A omega cosine omega t. And this one is negative A omega squared sine omega t. And these are the three equations that come from graphing the motion of a simply harmonically moving object. And we're going to use them next time round to start playing with this. We're going to put it together with the forces. It's going to be very exciting. So tune in next time. Thanks and good job, and keep it up. Now you might want to check this out in the book as well. There's a couple of practice problems in the book, and you should really make your own summary of these things so far and write it down and nut it out, and that way you'll keep it. Good job guys. See you soon.